Alright, in this video I just want to talk about the continuity of rational functions. So what does continuity mean and how can we use it to our advantage, the fact that simplified rational functions are continuous. So let's look at the notes. Simplified rational functions r of x equals p of x divided by q of x are continuous at all values of x except when q of x equals 0. And we know there are finitely many such values, at most n, if the degree of q of x equals n. There are at most n of those values. Now let's talk about what continuity actually means. For a function f of x to be continuous at a point x equals a, it means that the function f is defined at a, first of all, and that not only does this limit here exist, the limit as x tends towards a of f of x, not only does it exist, but we need to have the limit as x tends towards a of f of x equal to f of a. So let's just kind of draw a little diagram of what that would mean. Let's suppose that this is a and this is f of a. So we know our function takes this value at that point. And now since there are only finitely many points where simplified rational functions are not continuous, that means we can find some interval around a where there are no discontinuities inside that interval. So let's just seal it off. Okay, so inside this interval here, our function is continuous at all values. And so, well, just focusing on a for now, as x tends towards a from above or below, it means that the output values of f need to tend towards f of a from above or below. The point is they need to get closer and closer towards f of a. And so whatever the curve looks like, the values on that curve need to get closer and closer towards f of a. And since the same thing is true for any other point, say b, inside, so this is f of b, then we have the same thing going on for the curve at b and every other point inside this interval, which means we're going to have a curve that we can just draw, well, without taking a pen off the page. And that's the main point here. If f is continuous at all points x in an interval a less than or equal to x less than or equal to b, it means we can draw the function curve without taking our pen off the page. So we can draw the function curve without taking the pen off the page. Just a reminder that that's only for simplified rational functions. If r of x was non-simplified, like r of x equals p of x s of x divided by q of x s of x, and then if we have s of x1 equals 0, as we talked about before, there's going to be a discontinuity at x1. It would still look like r of x equals p of x divided by q of x. It would still look like that graph, except there would be a hole at the value x1, and then well, I guess this point would be p of x1 divided by q of x1. Assuming q of x1 doesn't equal 0 there. Anyway, so that's just how we can make full use of this sketching simplified rational functions checklist. We have all this information that we can find about our rational function, and then combine it with the fact that except at the vertical asymptotes, we can draw it without taking our pen off the page. And then apart from that, just getting used to the general shapes of these kinds of functions. Those are the techniques that we should be using to sketch these rational functions in further maths. By the way, here's a bit of optional extra reading if you're interested. So this is the real definition of a limit. In our high school maths, we don't really get into this. We just sort of describe a limit as what happens to the function as x gets closer and closer to c. What does the function get closer and closer towards? So let me write that down. As x gets closer to c, what does f of x get closer to, if anything? And the only problem is we don't really define what does getting closer to it actually mean. Here, using the real definition of the limit, this getting closer thing is properly defined. And the definition is as follows. Let f be a function defined on a subset D of the real numbers. Let C be a limit point of D, and let L be a real number. The definition of a limit point is down here. To say that C is a limit point of D means that for all the intervals a, b, which are a subset of R, that contain C, there is another point of D in a, b. So C is a limit point of D and L is a real number. Then we say that the limit as x tends towards C of f of x is equal to L if for every number epsilon, this is the Greek letter epsilon, E-P-S-I-L-O-N, so epsilon greater than 0, there is another number delta greater than 0, such that for all x in D, we have that if 0 is less than x minus c less than delta, then f of x minus L is less than epsilon. So it's kind of like a game, if you think about it. You give me a number epsilon that's greater than 0, but you can make it as small as you want. And no matter how small you make this epsilon, I can find a delta that is also bigger than 0, such that if I have x minus c in modulus less than delta, but bigger than 0, we don't care about what happens when it's equal to 0, just for all x such that x minus c in modulus is bigger than 0 but less than delta, then we have the function value at x minus L in modulus has to be less than that epsilon value that you gave me. So yeah, I invite you to have a think about this, the real definition of the limit. If you do math in university, no doubt this is going to come up if you go far with it. Or even if you just get into it at all, this is probably going to come up there. And so once you've wrapped your mind around this, you can use this definition here to prove things like the limit laws. For example, if the limit as x tends towards c of f of x equals L, and let's say the limit as x tends towards c of g of x is equal to p, then the limit as x tends towards c of f of x times g of x, we can prove that that's equal to L times p. So things like that. This definition can be used to prove the limit laws. So I encourage you to do that as well as an optional exercise. It's not part of further math.